So J.J. Thomson made what was called a cathode ray tube. This is a photograph of one. Here's an illustration. So it's a glass tube that's partially evacuated. There's just a little bit of gas in there. And we have electrodes at each end, and we apply a high voltage. There's no wire or anything between. There's just a little bit of gas in there. But if you apply a high enough voltage, you can get you can get something that shoots from one end to the other. And it causes the gas to glow a little bit, and so you can actually see it. This end is called the cathode. It's negatively charged. This end is the anode. It's positively charged. And because these rays came from the cathode, they were called cathode rays. And this is a tube that made cathode rays, so they called it a cathode ray tube, right? So creative. Well, he did some studies with this very curious phenomenon, and he found that the particles in those cathode rays had some properties. They travel in straight lines, and they were independent of the composition of the material they originated from. So if the cathode was tin or copper or gold, didn't matter, the cathode rays had the same properties. He also found that they have a negative electrical charge. So we need to understand how electrical charge works. An electrical charge is a fundamental property that some particles have. Opposite electrical charges attract each other. Like electrical charges repel each other. And in this way, electrical charge behaves very much like magnetic charge. It's not really charge, but you think of two magnets. Magnets have a north pole and a south pole, right? If you put a north pole with a south pole, they will pull together and stick to each other. They are attracted. If you try to put two north poles or two south poles together, you'll have to push really, really hard, and depending on how strong the magnet is, you might not be able to squeeze them together because they repel. So these positive and negative charges behave like that. If you have a +1 charge and a -1 charge, and you have those things together, then overall the thing is neutral, has no charge. So these rays travel in straight lines, but if you apply an electric field and a magnetic field, you can cause the beam to bend. And how far it bends is affected by the mass of the particles and the charge that they carry. So he couldn't determine either of those separately, but he could determine the ratio. So the ratio of charge to mass was negative 1.76 times 10 to the 8th coulombs per gram. Coulomb is a unit of electrical charge. What was really, really crazy about this is that charge to mass ratio implied that those particles were 2,000 times lighter than the smallest known element. So those particles cannot be atoms. They must be little pieces that came off of atoms. The indestructible atom could be chipped away. What? That was crazy. What he had discovered were electrons. Electrons have negative charges. They have very low mass. They are present in all atoms. Hydrogen only has one electron, but every single atom has some electrons. So this was the first evidence that elements are formed from the same particles. So before they thought, well, an atom of hydrogen and an atom of helium, they're just like two completely different things. And now they're like, oh, but they both have electrons somehow inside of them. So all the different elements are composed of the same smaller building blocks. An American scientist named Robert Millikan did an oil drop experiment, and from this he deduced the charge of a single electron. I have a video for this one too, but I'm going to try to explain it a little bit first, and then we'll watch the video. So this is an atomizer, just like a perfume atomizer, and it takes this oil and makes a spray of little tiny oil droplets. And of course, those are subject to gravity, and so you spray them out and they begin to fall. This plate up here had a tiny hole in the middle. And so the oil drops that happened to fall right where the hole was would keep going and go straight through. The rest of them just kind of made an oily mess up here. So down here is another plate, and they applied an electric charge. So this one's negative and this one's positive. And so we have these little oil droplets falling through this space. There's a light so they can see what's going on, a microscope. And they're shooting it with ionizing radiation, which is going to cause those oil droplets to have a negative charge. If you get it just right, the balance of this, the magnitude of this field relative to the charge on the drop and its mass, you can actually suspend that oil droplet in midair, keep it from going up or down. And from that information, they could do some calculations that led to calculating the charge of a single electron. So I'm going to let the video explain that. So some of you who, like physics and math and stuff will find the equations and stuff interesting. Many of you will not find it interesting. It's okay. You say, oh, wow, they did that. Okay, great for them. I'm not going to make you do any of these calculations, but it's really pretty cool. I mean, this is 1909. Where was technology in 1909? They knew what electricity was. Did everybody have electricity in their home? No. Did everybody drive cars? Radio, TV, telephones, not invented yet. I mean, not exactly the dark ages, but compared to now, it was pretty dim. It was pretty dim back then. And so he's doing this. It's pretty neat.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
Yes, that's exceedingly small. Any questions? So this kind of says some of that again. It did calculations using the electric field, what strength of electric field was needed to stop the drops from falling. They could measure the velocity. There's actually well, the mass of the droplet, there's two ways. The video mentioned the terminal velocity of the particle. You could also do it by measuring the radius and the density of the oil particle. And so they were able to calculate the charge on each drop. Now, different drops had different charges. But all of those charges were a multiple of this number. So this is the common factor to all of those charges. And so this must be the smallest possible charge. Then they calculated the mass of an electron, which is just mind-bogglingly small. As a decimal point with 27 zeros and then 910 grams. Very small.